Good afternoon. Post-lunch session and last session before we all take our respective flights and trains to go back. This work has been carried out almost 2 years ago. But however, due to data insufficiency, and analysis, we were not able to publish it priorly. So this is an opportunity for us to really present this data to everyone here. Just to come to objectives briefly, we are interested in developing diagnostic devices, mainly for chemical and biosensors, and it has several applications. I don't want to go into the details, but most important is we actually work we make use of this U-bend fiber optic probe as a tool to realize sensors. So events and waves and the present on the surface of the optical fiber really help us in detecting refractive index changes, as well as if there is any chromophore like a gold nanoparticle present on the surface. So what happens is if it is a straight fiber, the evanescent field is less. So this is the evanescent field and the depth of penetration, field strength. And so both are less in case of straight fiber. And if you bend the fiber like this, you will actually have a better evanescent field, and that's what we exploit in getting the a more sensitive sensor in place. So when we so this is 200 micron core fiber. So the silica core is 200 microns in diameter, and when we bend it, it is less than 1 mm. And the light propagation is seen here. So the light typically is always propagating. Most of the light propagates at the center of the fiber. The moment it reaches the bend region, so about 40% of light is lost. However, 60% of the light continues to propagate. However, not through the center, but at the periphery, especially the outer periphery. So because of this reason, we have a lot more evanescent wave interactions, light matter interactions are possible, and that's how we'll be able to detect any chromophore particles, nanoparticles like gold nanoparticles very efficiently. So, and this is one example, one can actually see if the probe is put in nanoparticle solution, if the nanoparticles come and bind, you can actually see the spectrum of gold nanoparticles over time as they bind. So real-time binding response is possible. Spectral analysis is possible. Refractive index sensitivity can be possible. And one interesting thing is it just needs one LED and a photodetector on either side. So you don't need any complex circuits. So with this platform, we actually have developed various applications, sensors for various analytes, starting from ions to all the way to pathogens. So today, however, we'll discuss about biosensing, especially COVID sensing. So what earlier you have seen how the fiber was bent using a candle frame. So this we have automated over last 3 years. So this is the fiber bending machine that we have realized in the laboratory and transferred it to our startup. It can make about 100 probes in a minute, in an hour. And we also have developed handheld devices with the independent display possible. They can be powered using USB or battery. So this is the readout device and this is the cartridge. So cartridge looks like this. So this is the cartridge to hold the fiber, and this is the sensing region. The bend region is the sensing region. In addition to the single mode single channel systems, we have also developed multi-channel systems, mainly to make sure that multiplexing is possible, biomolecular interaction analysis is possible. So we call this, when we use these probes, and we simply perform a sandwich immunoassay with gold nanoparticles as labels. So that means 2 bioreceptors are going to sandwich the analyte, and one of the top bioreceptor or capture detector antibody, we call it as, is typically tagged to an enzyme or a nanoparticle. Here we are using a nanoparticle, mainly because the probes are sensitive to chromophores. So the way we perform is very simple. we actually take an analyte sample, and then add the reagent which has gold nanoparticles conjugated with detector antibody. Leave it for 5 minutes, mix them and leave it for 5 minutes, and then dip the probe containing the antibodies, the capture antibodies coated on its surface into this mixture. So, and leave it, and you can actually see real-time binding response. So you actually have a sandwich immunocomplex formed on the surface of the fiber with gold nanoparticles very close to the surface. As soon as the gold nanoparticles are on the surface, we actually start seeing the absorption. So this is how the optical absorption goes up depending on the concentration of the analyte in the solution. And the dose response curve one can actually generate like this. And we see that any analyte, for example, here a model analyte is used, human IgG. When we use this, we were able to go down to 1 femtogram per ml of concentrations that comes to about 6 attomolar concentration. So this is a very good result. This is a surprise to us, and we realized it way back in 2016. But however, we published it only in 2020. We took some time to understand and benchmark the results and then published it. And people were really not convinced with the result. And however, you see that we did take these other analytes and show the same response. So what is more important here to note is when you have a combination of good physics, chemistry, and biology and nanotechnology, you can actually make things much more simpler for you. So here what you see is that such a attomolar analyte detection is possible in simple 2 steps. One step where you actually mix the reagent with sample, and the second step is simple incubation step. There's no washing step as well. And the setup that you need is simple LED and photo detector. There is nothing more beyond this. So in comparison, the first iconic paper published in Science on attomolar analyte detection actually uses a lot of multiplication steps. So in fact, you don't need to do so much of hard work when you use right sensors in place. So we, as I said, it is not just by chance. We actually realized attomolar analyte detection sensitivities using what we call it as Plasmonic fiber optic absorption biosensor for LAM, lipoarabinomannan, for a TB case as well. So LAM is present in urine in TB-infected patients, active TB-infected patients, urine between 1 to 10,000 femtogram per ml. And we did the same assay where we took the urine, simulated urine here. We didn't have permission to use urine samples, actual urine samples. So we spiked the urine with simulated urine with LAM, known concentrations, and then realized the assay. So this is the dose response. Here also we see that because of the antibody combinations that we took, we were able to go down to only 58 or 60 attomolar concentrations, not 6 attomolar concentration. It depends on antibody antigen affinity as well. So, and then of course, we did write a review paper on attomolar analyte detection sensitivities. If you're interested, you can refer to Chemical Society Reviews RSC journal. We did this for pregnancy-induced hypertension preeclampsia however, on a plastic optical fiber, mainly because we used PLGF, placental growth factor, as a biomarker for preeclampsia. You do have conventional techniques like Roche setup, which is a centralized laboratory-based test. It cannot be taken to primary healthcare center. So one of the major problems is, of course, they go for certain other markers or a ratio of markers. What we wanted to see is we want to make it simple based on the scientific literature already available. And we did see that we need to detect 30 picogram per ml in serum. So we went ahead and did the same assay. However, here we have used polymeric optical fiber. The chemistry is again different, not a silica fiber. So polymeric optical fibers are going to give less sensitivity, but we are still okay with that. So what we did is we did realize that we were able to go down to 0.2 picogram per ml of PLGF detection. So with that preliminary result, dose response curves, we went ahead and did clinical sample analysis. We were able to distinguish positive and negative samples, 11 positive and negative samples each. Not a big number. We need to do more sample analysis up to a number of like 100, 200, 500. Then our CDSCO can look at these results. So we'll be doing that in future, near future. So coming to COVID, you all know and we all forgot about COVID, thanks. But however, we really made a lot of progress, a lot of good understanding we have developed over those years. So whenever we have such kind of infections, respiratory infections, either one can access the sample through nasal or oral regions. So get the swabs, simply dip it in extraction buffer, and you have the virus lysed, and then protein comes out of into the solution. So you don't need to pre-process the sample. Just you use this just like that. Just take 50 microliters or 25 microliters of this extract, and then add another 25 microliters of this label, and then 5 minutes of incubation. Mix it and then incubate it for 5 minutes, and dip the probes, and you have the assay going. So this is for a change, we have developed a point of care device, a handheld device with an independent display. Both LED and photo detectors are already in place here. And this can be an independent display or can be interfaced to a computer. So what it has got is basically it has an LED with a constant current driver circuit, photo detector with an amplifier circuit, a microcontroller to control the LED currents as well as get the PD output and display it or pass it on to computer. So this is the response. The POC device was able to detect N protein, recombinant N protein, down to 10 picogram per ml in solution. So these are spiked samples. So this is the response for 10 picogram per ml. And then now we are sure that the POC is working, point of care device is working. So we use this POC for clinical samples. Again, here, not many samples. By the time we started, COVID has ended almost, thanks to those terrible days. So we took 10 positive samples and 5 negative samples, and we see that some 2 samples we are not able to detect them as positive. So of course, some limitations with respect to the probes, maybe, or the sample itself. So this tells us that this POC device is actually capable of detecting concentrations down to very low level where even the current ELISA or sophisticated techniques are not able to detect. So with that, I thank you very much for your attention. And if you have any questions, please let me know.